Dear colleagues, let me introduce my report, Artificial Intelligence in Time Management Leveraging Machine Learning for Adaptive Scheduling by Alexandra Bulgakova, Vyacheslav Zosimov, and Viktor Perederi. The work describes a system that analyzes a large volume of data on users' daily activities and habits to create individual plans and schedules. This system employs machine learning algorithms to identify repetitive patterns and predict the optimal distribution of tasks. Furthermore, studies focus on developing systems that consider the emotional state and overall well-being of users, offering recommendations to support a healthy balance between work and professional life. Moreover, advancement and NLP and language understanding contribute to development of more intuitive and convenient virtual assistant, which can assist in planning and managing the user time. In comparing the core functionality of personal time management apps available for the Google Play Store, we are now focusing on incorporated AI into our program. This AI enhancement aims to significantly improve upon the existing features offered by popular applications by introducing intelligent scheduling, task optimization, and so on. This analysis excludes brand-specific apps like Notes for iOS and so on. Based on the competitive analysis, a list of functional and not functional requirements for the main application was formed. Practice shows that implementing an overlay extensive feature set now not always justified as the app becomes less optimized and development becomes more expensive and lengthy. AI elements will be added to this application next, aiming to enhance efficiency and user experience while maintaining optimal performance. Unlike broader project management tools that may require sharing data across teams or even externally, our system will operate solely on personal data that is not shared with with the third parties. The AI will be trained on the user's device, meaning all personal data used to train and refine the AI algorithm will remain private and under the user control. The ecosystem will store and use three types of data: nodes, attachments, and configuration files. The configuration files is represented by a separate XML file. Attachments are stored in a separate folder as files of any type. The diagram shows classes of three types: entity classes, boundary classes, and control classes. Entity classes are key abstractions used in model. These include node and node list. The node class presents a specific node, contains its name, content, and tag, as well as operations for working with them. The node list class is a list of nodes designed to store an array of node class objects. Boundary classes serve as intermediaries in the interaction of external objects with the system. In this diagram, the boundary classes are GUI for user interaction with the program and not data model. For interaction with the database, control classes provide coordination of the behavior for objects in the system and serve as the mediator between boundary classes and entities. The control classes in this diagram are did controlled, which provide the ability to edit a node, and node list controller, which provides management of nodes in the node list. During the development of the application model, a state diagram for the node entity was designed. Upon creation, the node transitioned to the created state. At this point, all its attributes except for the identifier are empty. The diagram on slide describes the node editing process. The user can perform one of the following actions. As you see, when highlighting text in the node's title field, it can be changed. A new title can be entered. After that, the node is saved and the user continues working with it. When managing the node, the user is presented with three options: add a new tag, change an existing one, or delete it. After any action is taken, the node is automatically saved and the user continues working with it. When highlighting text in the node content field, the user is presented with the list of options. The adaptive planning based on AI features will use machine learning algorithms to analyze the user's nodes collect over a certain period. The system identifies repeated behavior patterns. Based on this data, the system automatically generates a suggested schedule of actions for the following week. AI analyzes not only the time and date of events, but also their context. For example, if user regularly records a meeting with a certain group of people or specific tasks on certain days of week, the system will identify this as a pattern. Over time, the system becomes more accurate. Slide presents the algorithm of the adaptive planning work. This diagram shows the sequence of steps that include data collection and processing, application of machine learning algorithms to analyze patterns in user behavior. This algorithm can be used as a basis for developing a system that automatically generates a schedule based on the analysis of user nodes. The proposed system utilizes a layered approach where the output of the neural network is specifically of a long short-term memory LSTM model feeds into a clustering algorithm. The LSTM is staked with analyzed temporal dependencies in the user behavior data to predict future patterns. Then this schedule should adapt to newly observed patterns as data occurs over time. The steps of the algorithm, which are presented on slide. The table on slide presents summary testing results where 180 data points capturing a range of user behaviors and present preferences. The analysis identified key recurrent events that include essentially daily routines such as coffee breaks, gym sessions. Additionally, it discerns subtle patterns, notably preference of afternoon calls and quiet evening. The LSTM model employed in this study consists of two layers, each with 15 units and utilizes tag activation functions to add non-linearity to the learning process. The combat of overfitting and dropout is applied at the rate of 0.5 between the LSTM layers. This architecture was chosen for its ability to effectively capture and model the time series data generated by user interaction with the system. The number of clusters was determined using the method which evaluates the consistency with clusters of data. Data was collected over a 2 months period from a group of volunteers to use the system under an agreement ensuring data privacy and ethical use. The algorithm efficiency differentiated between high energy tasks, optimal places in mid-morning when users are likely to be more productive, and low energy tasks between suited for the end of the day, aligning with natural dips in energy and concentration. The predictive accuracy of the model reached 94%. The results confirm the effectiveness of the proposed adaptive planning model, showing its capability to accurately discern the depth of complex user behaviors. The use of clustering and regression techniques helps the system predict and organize tasks effectively, aligning with user preferences and optimal productivity times as supported by the positive test data outcomes. The clustering approach facilitated by the method to determine the optimal number of clusters further enable the system to segment the user behaviors into meaningful categories. Future research could explore the integration of context-aware computing to enhance the system's ability to adjust recommendations based on real-time user context, such as location or current activities, to enhance accuracy and mitigate issues associated with imprecise or incomplete data. It is proposed to integrate fuzzy logic into the system. Thank you for your attention.